Okay, let's start with our first example, which is number 2 in your exercises. And this is our given differential equation, and it says find a power series solution of this equation, then determine the radius of convergence, and then use the series in equations 5 through 12, so I believe that's page 195 in your book, to identify the series solutions in terms of familiar elementary functions. Okay, so there's about 3 steps here. So here's the kind of main idea. These solutions are going to be power series solutions. So let's start with assuming that our solution is going to be a power series. So we're going to let y equal the summation of Cn x to the n. Okay, and we're going to start at 0 and we're going to go to infinity. So here is our summand, our infinite sum. And our differential equation, the order is 1, so we're definitely going to find the derivative. So if we take the derivative of y, right, of this guy, then, so I'm going to write the summation. Using the power rule, right, I'm just going to bring down the power. Cn is a constant, and then I'm going to subtract 1. And here, right, our index in this case, right, it starts at 0, but this one doesn't start at 0. If we did put n equals 0, this wouldn't make sense because 0 minus 1 is negative 1, and we're working with series, and series are positive. We have positive exponents. So here we have to start at 1, and we're going to infinity. Okay, so that's usually the first step, right? Let y be that power series, find y prime, and now let's substitute y and y prime back into the equation. So, right, these guys, let's put them back here. And actually, I should have done this in the beginning, but it's not a big deal. But I'm going to go ahead and subtract 4y because I want the right-hand side to be 0. And you'll see why in a couple of steps, because I want to use the identity principle, and in order to use that I need my right hand side to be 0. Okay, so let's substitute. So my y prime is, again, substitution, n equals 1 to infinity minus 4 times y. Well, my y was, I chose it to be this power series, and it's equal to 0. Okay, so again, here is my y prime, right, minus 4 times, and then this is my y. Okay, so here we want to, the goal is to find these coefficients, right, and there's going to be infinitely number of coefficients. And one of the things that you learned in series in your probably first or second calculus course is your indices have to match, but also when you're working with these variables, right, your x terms, you have x to the n minus 1, okay, and x to the n. So after substituting your y and y prime, okay, the first thing you want to do is you want to match these guys. You want this to be x to, one single power, like this n. So here, I'm going to go ahead and I'm going to maybe choose this color. So I'm going to let x be k. Okay, and k is going to be my dummy variable. Use dummy variable, and a dummy variable in math, it actually is a math term. A dummy variable is basically just a placeholder variable. So if I let, okay, so I'm letting k be n minus 1. Okay, so if we solve for n, then that's going to be k plus 1. Okay, so I want to use this to rewrite this guy. Okay, so I'm going to write my sigma. N is k plus 1. So I'm going to replace n with k plus 1. And let's see, I have Cn, so C k plus 1, since again n is equal to k plus 1. And then x to the k, so I let n minus 1 be k. Okay, so now where does my index start? Well, we're working with k, so I have to start with k. And originally I had n equals 1. Well, if n is equal to 1, then k is 0, right? If we input 1 here. So we're definitely starting with 0. So I rewrote that using a placeholder variable or a dummy variable. And I'm going to rewrite this guy since I haven't done anything with it. Okay, so now we have nice powers of x raised to, right, 1, I guess, place value, right? There's no, n minus 1, it's just k. And usually we want our indices, we want our indices to match, and I mean they do, they both start at 0. Okay, now here, I know this is going to be a little tricky, but here I'm going to write my sigma. I'm going to replace my k's with n's, okay, and I'll explain why in a bit. So n plus 1, c n plus 1, x to the n. Okay, the reason I'm doing that is because I'm working with n, so I want to leave it as n. If you want to change them all to k's, you can, but we started with n's. Now, one thing I want you to understand is that this power series and this power series are exactly the same. Oh, and actually forgot to write my index. N is equal to 0. Now, if you want to convince yourself that it is, these are actually the same, well, just go ahead and work it out. It's actually a great idea to, really understand this and this using this dummy variable. Okay, so so I'll start with the first one, right? I'm going to use this guy, and if k is 0, what do I get? If k is 0, I get 1 times c1 x to the 0 is 1, okay. Plus, what if k is 1? Well, I get 2c2 x to the 1 plus, and then dot, dot, dot. Okay, now let's do it for this guy. What if n is 0? If n is 0, then I get, again, I'm using this guy. I get, let's see, 1c1 x to the 0, which is 1, plus, okay, what if n is 1? Then I get 2c1 plus 1 is 2, x to the 1, and then if you keep going, right, these guys are exactly the same. Again, the dummy variable is just a placeholder variable, so that's why I'm allowed to replace my k's with n's. Because the math proves it. It's very nice. Okay, so from here, so this was kind of a side note to convince yourself, or convince you that they are the same power series. Let's use power series operations. Right, to simplify this a little bit. And this is on page, let's see, 196. And basically what the power series operations say is, one of them is we have, okay, so if we have one power series, and I'm going to call this guy, and I add another power series, so of course starting at 0, bn x to the n, I'm allowed to say this is the summation of an plus bn x to the n, and n is going from 0 to infinity. So this is what I'm going to use. And again, if you want to convince yourself, write out the terms, and you'll see you're going to actually get the right-hand side. If you write all this out, you will get the right-hand side. Okay, so using these operations, let me just go ahead, and I wrote a lot of side notes here. So from here, okay, I'm going to write, so summation of 0 to infinity, forgot my infinity there. Let's see, I'm going to factor out x to the n, that's what we're really doing. We have n plus 1 Cn plus 1 minus 4Cn x to the n equals 0. All right, I'm writing everything except my x to the n, so 4 and that guy. Okay, so now that I used the my power series operations, now I can use, so by the identity principle in your book, I think also on page 196, I'm allowed to equate the coefficients, just like we did in chapter 2, but again, here we have an infinite series. So I'm just going to equate these guys. So n plus 1, Cn minus n plus 1 minus 4 Cn is equal to 0. Now our goal is to obtain a recurrence relation because we want to determine what these coefficients are. So here I'm going to go ahead and solve for for Cn plus 1 because I want to write it in terms of Cn. So let's do step by step here. I'm going to bring this over, and if I solve for Cn plus 1, I get 4Cn over n plus 1. Okay, this is my recurrence relation, right, in terms of Cn. You always want to write it in terms of Cn. You can solve for Cn and write it in terms of Cn plus 1, but it's much easier when you're working with, when this guy is larger than this guy, specifically the subscript. I'm going to stop here and continue in the next video because these are very tedious problems. So we'll explore this pattern and hopefully find the coefficients.